You are warmly welcome to IETV. Today I am going to teach you on shear force and bending moments. This is the first video on this lesson. If you are learning something, don't forget to subscribe me. This is IETV, International Education TV. Let's quickly move to the lesson. So today I am going to teach you on relationship between distributed load, shear force and bending moment. Let's consider a beam subjected to a distributed load which is non-uniform. You can see this beam in this picture. The distributed load is not uniform. That is why we have denoted it as W into X, and also we have considered this AB portion because when we are dealing with internal forces like shear force and bending moment, we have to consider an internal section. Otherwise, we can't derive a relationship between shear force, bending moment and distributed load. That's why we have considered internal part of this section, which is AB, and the length is delta X, which is very small. And we have considered the direction of X is towards A to B. The section, I have enlarged that section, AB section. Here you can see that here M means bending moment, S means shear force. We assume that the shear force on AB section at face A is upward direction and bending moment is anti-clockwise. And also you can see that from here to here the total load has increased due to this load accumulation. So that's why we have increased shear force as well in that face B, S plus delta S. And also we have increased bending moment as M plus delta M. The reason is from here to here the total load increases, but the direction of these forces at face B on this small section is opposite to loads at A. You can see clearly here. I will tell you what the reason is. Due to this AB section, you see that the beam divided into three sections. This section, AB section, and this section at the right hand side. So we assume that this shear force is upward direction on face A of the small section. Accordingly, in this section, third section, you can consider this third section, face B of the third section, that shear force should be upward direction, because we have considered in this side the shear force is upward direction. Accordingly, the shear force on face B of this long section is upward direction. Likewise, the bending moment, direction of bending moment is anti-clockwise on the face B of this long section. You know that Newton's third law, according to Newton's third law, loads on face B of the small section is opposite to the loads at face B on this long section. That is why this opposite to load at A. That's why these loads are in opposite direction to face A. So now you can clear this picture, and also we have indicated this intensity here. The load intensity is W here, and also here W plus delta W. The delta here delta X, delta W, delta S are small ones. Now you can clear this picture. Now let's move to our derivation. We can consider vertical equilibrium because you know that this beam is in equilibrium. So therefore, by resolving the loads downward direction, you know that in downward direction S plus delta S is positive. In this picture, S plus delta S is in downward direction. Therefore, this S plus delta S is positive, and also this S is minus, and this we have to consider this W, this distributed load, resultant force of this distributed load. In here it is W, in here W plus delta W. You can take this average load average intensity over this section, it is W plus delta W over 2. It is average intensity, but we have to get the total load. Therefore this intensity we have to multiply it by delta X. So in this case, in this equation, this S plus delta S minus S, this is W plus delta W over 2 means average intensity over the length of delta X, but here we have multiplied that average intensity by delta X to take the resultant force. It is in downward direction, it is positive. According to this expression, we can take delta S is equal to this expression. So you know that we can neglect this second order terms. That means when we remove these brackets, so we have to multiply this delta W into delta X. These expressions, that means delta W into delta X, those are very small ones, because delta W is very small, delta X is very small, but the multiplication is also very small. Therefore those multiplications we are called second order terms, they are neglected. That's why we cancel this delta W into delta X, only consider this 2W into delta X. We cancel this delta W into delta X. After cancelling this delta W into delta X to 0, we can take delta S over delta X is equal to minus W. That means in this case, you know that this delta X is very small. If we consider that delta X is limit to 0, in here I have considered delta X limit to 0, delta S over delta X is equal to ds over dx, ds over dx. In that case, we can write ds over dx is equal to minus W. That means the rate of change of shear force at a section of the beam is equal to minus times the load intensity at that section. If you don't understand this, you can easily understand while we are doing calculations on this regard. Then we took that relationship between intensity, load in external load, distributed load in intensity, and the shear force. Then consider that bending movement. So therefore we have to consider rotational equilibrium of the element. So in this case, you know that let's move to that picture again. In here we consider that clockwise movement positive, that m plus delta m is positive here, this m is negative here, and also this s, the moment due to s is s into delta x. You know that we have to multiply the force by the perpendicular distance to take the moment. It is also clockwise positive. So moment which create due to this that resultant force of the external load is anti-clockwise. Therefore that is minus. So let's quickly move to that equation. In here I told you that here m plus delta m is positive, in here m is minus, and s into delta x, this moment due to shear force at phase A is positive. And also here there are two sections, in this one and this one. I will tell you what is this, what is this. This whole expression is due to moment created by the external distributed load. So in this case, this two portion, we have divided this distributed load into two sections. When we draw a line here horizontally, so therefore you see that this is a trapezoidal load, so we can divide it into two. That means this rectangular and this triangular load and this rectangular load. Then in the rectangular section, the intensity is W, it is constant. In here to here is constant load over delta X. The constant load means the load, total load is W into delta X, which is at the center of this AB section. That means the resultant force is W into delta X at the middle of this section. Resultant force W into delta X at the middle of the section. So therefore the moment is W into delta X total load, delta X over 2 means the length from AB to the resultant force, the length from face B to the resultant force. In that, the other part you can see here, this other part is due to the moment which created by this triangular load. Here it is 0, and here you say horizontal line, when we draw a horizontal line here, this is W, because this side is W, therefore this side is W, and the length of this side of this triangle is delta W, because W plus delta W minus W, which is the length of this side. This side, the length of this side is delta W. Here 0, average intensity is 0 plus delta W over 2, and it acts at the centroid of this triangle, which is 1/3 length from this side. That means from here to here length delta X over 3. This you can see that here half into delta W means average intensity. That intensity over delta X length, that's the force. Half into delta W into delta X is the force, and delta X over 3 means length from face B to the resultant force, which act at the centroid of that triangle. It is equal to 0 because the section is in equilibrium. You know that I told you earlier that second order terms, that means delta X into delta X, delta W delta X into delta X, such terms we can neglect. So therefore by neglecting that part, we can write delta M over delta X is equal to minus S. That means when delta X limit 0, delta M over delta X dm over dx is equal to minus S, which is rate of change of bending moment is equal to minus into shear force at that section. Now you have derived main relationships between distributed load, shear force and bending moment. So if you can't understand this lesson, you can understand by doing examples I'm going to teach you at the next videos. So let's again consider this dm over dx is equal to minus S. We can differentiate this dm over dx again by x. So therefore we come up with d over d squared m over dx squared is equal to minus ds over dx, which is equal to w according to our early proof. It ends up with m over d squared is equal to w. This is also very important one when we are doing calculations, and also this is the most important one that you should keep in your mind. Those above derived equation cannot be used in everywhere of the beam. So let's consider this AE beam. In this picture you can clearly see that AE beam, we can use that equation from A to B, B to C, C to D, D to E, but you can't use that equations from A to C because there is a concentrated load here, and also we cannot use that equation from A to D and also A to E. We cannot use those equations, but we can use from C to D, C to D. We can use A to B, B to C, C to D, D to E. But you should keep remember, when there is a point load at the middle, we cannot use that derived equation. So you will easily understand those things when you are doing calculations. So I invite you to be with us in next videos.